A while ago, I was thinking about Euler's identity, the famous e to the I pi is -1. Now, one thing that I've always been curious about is the pi in Euler's identity. Now, if you don't know, the pi is supposed to be a radian measure. To see why, let's expand this. Okay, so we're plugging in an angle to the left-hand side and figuring out the output of that angle through the corresponding trig ratios. This always struck me as weird because e to the I pi was always advertised as numbers being put together in a certain way to make those numbers have a simple output. So to see pi being dependent on dimensions kind of ruined the fun. Like, wouldn't this also be a valid identity? Spoiler alert, it's not, and here's why. In finding out the answer to this question, we not only answer our beginning question, but we answer the more important and underlying question of why calculus only works in radians. First, why is Euler's identity true? Well, it has something to do with the McLaurin series expansion for sine, cosine, and e to the x. Let's write them all out. If you're wondering why functions that have nothing to do with polynomials can equal polynomials, there's a nice video by 3blue1brown that I've linked in the description. Anyway, with some simple manipulation, we can see that e to the x is just barely sine x plus cosine x. The coefficients seem to have the same values, but the coefficients in e to the x are always positive. So to flip the coefficients, we replace x with ix. Doing this introduces the signature flipping of signs, but we now have imaginary coefficients. So to fix this, we can replace the sine x on the bottom side with I sine x. And we can see that this equality holds. So now that we have a firm grasp on why Euler's identity is true, that still doesn't answer the question of why it relies on radians. I mean, sure, there are trig functions, but those could have just as easily worked in degrees. It seems that the reason these trig functions rely on degrees must have something to do with the McLaurin series, because that's the only source of error that could introduce this dependence on radians. To figure out the McLaurin series of a function, you need to know this fancy formula with factorials in it. The factorials come from repeated differentiation. If you're curious, the 3blue1brown video is linked below. Now, we know that the plane numbers in the series certainly don't rely on radians, and as discussed previously, the function itself doesn't rely on radians. So it must have something to do with the derivatives of the functions. We could also look at cosine, but sine and cosine have a connection. So looking at sine will probably give us the same information as if we looked at the series for cosine. Let's look at the derivatives of sine. And for the sake of simplicity, let's focus on the first derivative. Most calculus students probably know by heart that the derivative of sine is cosine. But why is that true? Well, as we do most of the time when finding the derivatives of functions we don't know, we have to use the definition of the derivative. The derivative is the instantaneous rate of change at a point, or writing it out in limit form, the h is supposed to represent a tiny nudge in the function. So we are taking the limit of how the nudge changes the function divided by the nudge itself. And we are taking that as the nudge approaches 0. Plugging in the function for sine gives this. It doesn't look like we can simplify any further, so let's try to expand. The sine of x plus h can nicely be rewritten by a trig identity. By expanding, we can factor the numerator and split the limit into two fractions. While we're at it, we might as well just use the limit laws to split this into two individual limits. Now notice that any function in terms of x doesn't change as h approaches 0. To get a better intuition of this, suppose we have x to be some concrete finite number, like 3. Then these two functions involving x don't change as h goes to 0, so we can nicely pull them out. Now we are left with these two infamous limits. Because the sine and cosine functions don't necessarily rely on radians, these two limits must be the source of calculus's dependence on radians. The limit involving cosine ultimately depends on the limit involving sine, which you can see here. So the limit involving sine must be the source of all this. So let's dig one step deeper to find out the answer to our question. To prove this limit, you can use some geometry. By constructing a unit circle and line with angle theta, we can construct these three shapes. By seeing that the area of these three shapes are in descending order, you can use some algebraic manipulation to get sine of theta over theta to be in between 1 and cosine of theta. Taking the limit as theta goes to 0 gives the result to be 1. Plugging this back into our original problem gives the derivative to be cosine of theta. Let's take a closer look at this geometry to see if the secret to our problem is hiding there. After all, the radian is interconnected with geometry. To find the areas of the triangles, we just use the definition of trig ratios for the sine triangle and the tangent triangle. But for this circular sector involving theta, we need to use a different strategy. We know that the area of the whole circle is pi because it's a unit circle. So this sector must be some fraction of pi. If we let theta to be in degrees, we have this fraction to be pi theta divided by 360. But if we let theta to be in radians, we know that this sector takes theta out of the whole 2 pi radians. Multiplying this by pi gives the simpler form, which is what we ultimately use to derive the value of this limit. So there we have it. It turned out that the reason calculus is in terms of radians is because radians allows for a simpler expression for area. Going a little further, if we graph the sine of x divided by x function on Desmos, and we let x to be in degrees, it turned out that the limit in degrees doesn't equal 1. Instead, it equals pi over 180. So if we introduce the limit into the limit definition of sine, we get this formula, which is a lot less clean. So you can see why calculus naturally tends towards radians. You can also prove this rigorously by letting theta in the geometric proof be in degrees. Okay, so now that we know why it only works in radians, that still doesn't get rid of the feeling that the most important equation in math still has a unit. Or does it? You see, radians are defined as a scalar. The signature definition of a radian, s equals r theta, makes radians defined as the scalar between s and r. Or in ratio form, theta is equal to s divided by r. The scalar is simply just a number. So radians don't actually have any units. So the most beautiful equation in math can remain beautiful.